Hello, everyone. This is Qing from the Climate Dynamics Prediction Laboratory in Purdue University. This video will serve as the pre-recorded version for the cyber training workshop held by Purdue University that is going to take place on June 1st and 2nd of 2021. Taking heat stress extreme prediction from the CMIP6 archive as an application case, we will cover 3 practical modules, including climate data access, processing, and visualization. In addition, we also have an extra video for how to use Cython to speed up your Python code. So there are 4 videos in total, and this is the first one for climate data access. Well, first, some background information. The intensification of heat stress is one of the major threats that global warming poses on human society. Heat stress is also a hot research topic. Lots of papers focus on this. Here are just some examples that has been published since last year. And I put this figure here in order to give a specific impression of the intensification of heat stress. Well, as we can see, for example, over the tropics, by the last 30 years of this century, there will be more than 3 months that are hotter than the annual hottest 3 days of today's climate. This projected heat stress intensification is expected to have various impacts, for example, leading to the reduction in labor capacity and social welfare. And this is kind of the motivation for people to do heat stress research. Okay, enough background information. Let's head into the first practical module, climate data access in Python. And we will first give a very brief lecture, and then we'll walk into the Jupyter Notebook to gain some hands-on experience. We're going to first introduce X-ray, which is a convenient Python package for geoscience data access and processing. Well, in this module, we'll focus on the X-ray's read and write syntax. We'll also briefly mention ZAR, which is an optimized file format for cloud storage. And then we'll introduce intake, which is another Python package that aims to offer a consistent data access API. And with the help of these tools, we will show how to access CMIP6 archive in cloud. And by the end of this module, you are expected to be familiar with X-ray read and write syntax, get an idea of the power of intake in facilitating data access, and also be able to access CMIP6 data in cloud efficiently. Well, many of you may already have experience in using CMIP6 data for your own research, and there are multiple ways to access them. And the first one, we call it the painful way. Basically, you need to first log on to a ESGF node. You click lots of options to narrow down your search, and you download a bunch of Vega scripts. Then you upload them into maybe the space in your university cluster, and then you run them one by one to download data locally. This sounds really painful, and it can cost a graduate student maybe 2 weeks to just download the data. So that's why we have the professional way by using the ESGF search API, which can enable you to search the data that you want, and the Open Depth Service, which is a data access protocol that can send data over the internet through HTTP. And the workflow is kind of like this. First, you pass in some arguments to do the query, and you will get a bunch of OpenDep URLs, and you can use X-ray to open them all at once. In this way, you don't have to download data locally. You only access the data through internet on demand. And this sounds much more convenient than the painful way, right? But we have an even better way, the smarter way, which is access CMIP6 data in cloud. And we will introduce the details of this workflow in the Jupyter Notebook, but you will find that it is very similar to the professional way. However, since there's no complex web service involved and the infrastructure is simpler, it is also substantially faster. But now we know that cloud computing is becoming more and more popular, and people tend to put their data and run their computation on cloud. Well, under the cooperation between PanGeo and the Google Cloud Public Data Site Program and the AWS Open Data Sponsorship Program, parts of the CMIP6 data are already available in cloud. and they are still constantly updating it. If you find the data you want is currently not available, you can send data request to the Purdue team, and they will upload for you with a higher priority. And I will leave the link of this data request in the comments of this video. And I also want to mention that the data in the cloud is stored as ZAR, which is an optimized format for cloud storage. It's used to store chunks and compress multi-dimensional arrays. And since the chunks are stored independently with each other, so you can read and write multiple chunks efficiently in parallel. Well, above, we are actually talking about how to access the file. But this is actually the first step of data access. And the second step is how to access the content of the file. And X-ray makes it really convenient by providing an easy read and write syntax, like the code below. It's just one line for read or one line for write. And you will see these codes in the Jupyter Notebook as well. And also X-ray offers an option to keep attributes when you do the calculation. So in this way, you don't have to add attributes manually. Now let's walk into the Jupyter Notebook. You can find the notebook in MyDualHub. You should be able to create an account in MyDualHub for free. And the notebook is under this FAIR, Climate and Water Science course. We click the notebook. And as an alternative, I also created a binder project for this tutorial. And everybody should be able to access that. And I will also put the link of the binder project in the comment of this video. Now let's begin. We will first briefly introduce the functionality of X-array. We import X-array and ZAR, and we will use the North American air temperature dataset in the tutorial of X-array. Now we have X-ray dataset, a labeled three-dimensional array with latitude, longitude, and time. Actually, this labeling is very powerful and makes X-ray very user-friendly and is the basis of many useful functionalities of X-ray. In this case, we have one data variable called air within this X-ray dataset. But in principle, we can have multiple data variables within one X-ray dataset. We also have some attributes information over here. We can access the data array inside this X-array dataset in this way, and we got a X-ray data array. And we should notice that so far, X-ray hasn't loaded any data into memory except some metadata. That's because X-ray is lazy and it will only load data into memory until we do some real calculations on that. That's why it only tells us that there are so many values over here with floating type, but without any actual values. We notice that the data set contains the temperature of 2 years, the 2013 and 2014. Now let's access each year separately and write them to our working directory. Now let's begin. We will first briefly introduce the functionality of X-array. We import X-array and ZAR. Then we use the North American air temperature dataset in the tutorial of X-array. You see that we got the X-array dataset over here. It's a labeled three-dimensional array with latitude, longitude, and time. And actually, this labeling is very powerful and it's the basis of many functionalities of X-array. It makes X-array very user-friendly for us. And in this case, we only have one data variable called air in this X-ray dataset. But in principle, you can have multiple data variables within one X-ray dataset. Here we also have some attributes information. Now let's access the data variable within this X-ray dataset by this. And we got the X-ray data array. And we notice that here it only tells us there are so many values with floating type, but without showing any actual value over here. That's because X-ray is lazy and it won't load any data into memory until we do some real calculations on that. There's some attributes over here as well. And also we notice that this is a data set for temperature for 2 years, the 2013 and 2014. Now let's access each year separately and write them to our working directory. We can use this toNetCDF function to output our data into the disk. And then we practice the read syntax of X-array using this XR open dataset to open one of the two files that we just output. And we got an X-array over here. Now let's do some calculations on this X-array. For example, we want to change the unit from Kelvin to Celsius degree. And we see that because we do some calculations and X-array will load the data into the memory. So we see some extra values over here. But the problem is we lose all the attributes over here. That's because X-array by default will only keep attributes in unambiguous circumstances. For example, over here, if we do any calculations on the temperature, we may still get a temperature and possibly with a different unit, like in this case. But it's also likely that what we get is not temperature, like maybe the saturation vapor pressure, which is a function of temperature. And X-ray is not able to determine this. So by default, X-ray will lose all the attributes. But we can set the option to inform X-ray to always keep attributes, no matter what we do. And here we set this option globally. But you can also pass in this keep attributes equals true with many individual X-ray operations as well. Now, after that, let's do the calculation again. As we expect, the attributes information are kept, but with the wrong units, and we need to change the units manually. We can access and assign units in this way. Yeah, you have the right units right now. In terms of the write syntax, X-ray can also enable us to write our data into a ZAR format by using this toZAR function. But if we want to use that, we need to first change TC from X-ray data array to X-ray data set first. Now let's check what we get over here. Yeah, we see that there is a directory called tczar over here. And let's check what's inside it. There are another 4 directories containing the data variable and the 3 coordinates. Let's check what's inside this data variable server directory. Yeah, there are multiple files, and each file corresponds to one chunk. So now let's use this X-array's open ZAR syntax to read in the data from the ZAR store that we just created. We will see that we got a chunked X-array data array. That's because when we output data into the ZAR store above, ZAR will automatically chunk the array for us. And we can also manually set the chunk size. In this case, we have 16 chunks correspond to the 16 small files stored over here. And also we have access to the size of each chunk. Well, as we have mentioned, in the above, there are multiple small files being stored in the ZAR store that we just created, and each small file corresponds to each chunk. And this kind of format is not preferable on an HPC cluster, especially when we want to move it. So in terms of this, ZAR also offers several other storage alternatives, and like this, the DBM style database. So we create the ZAR store first, and we use this toZAR syntax to write data into this ZAR store. And in this case, we need to close the store explicitly. Let's check what we get. Yes, we can see that we got this tczar BDB file, and this is a DBM database over here. And this one big file. In addition, another functionality X-ray offers us is being able to open multiple files in parallel. And that's very useful for us because climate data are often stored in the way that one file for each month or each year, and there are many files under a certain directory. So in this way, we can use this open MF dataset to open all the files all at once parallelly. And X-ray would be able to concatenate these files along the time dimension. And we see that we got a chunked array. And by default, they will be chunked in the way that each file corresponds to one chunk. And of course, we can always rechunk it. As we have mentioned, the labeling of X-ray makes it very user-friendly. And now we will see some useful functionality of X-ray based on this labeling system. The first one is easy index by label. For example, we can easily select any slice along any dimension like this way. Or we can do any statistics along a certain dimension. Here we calculate the annual mean. And over here, we first calculate the annual mean level, and then we calculate the zonal average within a certain range of latitudes. It's all very convenient. Another very handy thing that X-ray offers us is this group by syntax. For example, over here, we group the data by month, and then we can do any statistics within each group. In this case, we calculate the monthly mean. Here we only have 1 year data, but if we have 30 years, we can use this just one line code to calculate the climatological monthly mean values. And finally, we can use this resample syntax to downscale our data. Here, for example, we want to downscale our data from 4 times daily to the daily maximum. After we get a bit familiar with the X-ray syntax, now we try to access CMIP6 data in the cloud. First, we learn how to open a single ZAR store. A single ZAR store can be opened using X-ray's open ZAR function. And this function will take a Python native mutable mapping object as input. And this mutable mapping object can be acquired from a ZAR store URL using this sspec, which is a file system interface to work with remote file systems. Now let's see how it works. First, we use this sspec get mapper to create a mutable mapping object from this ZAR store URL. Now we pass in this mutable mapping object into this X-ray open ZAR function to read in the data. And this consolidated equals true will consolidate metadata objects into a single one, which can increase the speed of metadata reading. And it works fine. But in your mind, you may have a question that, where can I get ZAR store URL? You can first download the master CSV file, which contains a catalog that enumerates all available ZAR stores currently in the cloud. And then you can manually search this catalog using the pandas data frame search syntax. Let's look into that. We read in this CSV file as a data frame. There's lots of information over here. There's activity ID, the source ID, the table ID, the variable ID, and the ZAR store URLs, lots of useful information. And then we can query this data frame based on our needs. For example, over here, I ask activity ID to be CMIP and the source ID to be CSM2 and table ID to be monthly, and we only want the 2-meter air temperature. Then we get a small subset of a data frame based on our query. And we can access the ZAR store URLs like this. Now let's say if we want to access the last ZAR store, we can open this using the same syntax. First, create a mutable mapping object, then use this XR open ZAR function to open it, and it works well. Well, now you know where to find all the available ZAR store URLs, and you also know how to search the URLs that you want. But still, you need to open the ZAR stores one by one, and each time you will get an X-ray. And surely we can combine the multiple X arrays into a data set by ourselves, but still it involves extra work and it's not user-friendly. So is there a way to open multiple ZAR stores simultaneously and automatically combine them into a data set? The answer is yes, and intake-esm can help us to achieve that. Well, intake-esm is an add-on of intake, which is a Python package that aims to provide a consistent data access API. Before we introduce the details of intake-esm, let's get back to the slides to give a brief introduction to intake, what's intake, and how it works. Intake, as we have mentioned, aims to provide a general interface for loading data. I borrowed this particular slide from the talk by Martin Durant, who is one of the developers of intake. I think this slide is very straightforward to establish the motivation of this intake project. Now let's look at that. Well, for many people, when they are doing data analysis in Jupyter Notebook, this is often how their first cell look like, just read in some data. In this case, our data is stored as CSV files, and we use pandas to read in them. But maybe in another case, these CSV files are stored in a different place, so we need to change the code, or even they are not a CSV file anymore, like they are shape file, so we need to learn a whole different syntax about how to read in shapefile or many other type of files. And each time we need to completely rewrite this code. Now, as a data user, we want to ask a question. Do we really need to figure out this code every time? And then the data provider comes in saying that you shouldn't use this data at all because this is the old version and we already have a updated version. And the data provider needs to communicate with the data user and find a way to point them to a new updated version of the data. That's a lot of work for both the data user and data provider. And intake wants to make the life easier for both of them. As the data provider, they need to provide a catalog file, which is usually a YAML file that contains all the metadata information, such as the URL path, which is where the data is stored, and the driver information, which is CSV in this case. This informs the intake that this is a CSV file, and you need to use this CSV driver to read in the data. After the data provider finishes its catalog, they distribute it to a place that all the data users have access to. And then it would be very easy for data user to read in the data. It just open the catalog and then read. No matter it's a CSV file or shape file or other files, it just use the same syntax to read in the data. And someday, maybe the data provider wants to update the data. They just modify this catalog information, and the data user don't have to change their code at all. The reason why intake can achieve this is because of this plug-in system with intake in the center and different data loader drivers as plug-in. And the different data drivers can be developed by different teams that focus on different data formats. For example, if intake-esm is developed by NCAR that specializes on reading in climate mode output. And we also have intake-X-ray, intake-geopandas, and many others that can be accessed in the link below. Based on this plug-in system, intake would be able to identify the correct driver based on the information in the catalog file, and then call the driver to read in the data, even the user always use the same syntax. That's how intake provides the consistent data access API for all data formats. Now let's get back to the Jupyter Notebook. We have mentioned that intake-esm can help us open multiple ZAR stores at the same time and automatically combine them into a data set. Now let's look at the detail. We first import intake, and here we'll provide a link to an ESM collection file, which is a JSON file. And in this JSON file, there are a bunch of metadata information, including the logic of how the data stores can be combined into an aggregated data set. And using this ESM collection file, intake-esm would be able to connect a database, which is a CSV file that contains all the information of locations of data store and the metadata information. And all we use is this OpenESM data store function. And we can see that it's a catalog and it contains all the, and we can see that it's a catalog and it shows the amount of CMIP6 data that is currently available in the Google Cloud. And we can view it as a data frame. Now we can do some query on this catalog to search the data that we want. This is a Python dictionary we pass in the arguments to narrow our search. You'll notice that we ask for two variables, TAS and TASMax, and intake-esm provides functionality to execute this query against the catalog. We need to use this search function and pass in the query dictionary that we just created. What we get is a subset of the catalog. We can also view it as a data frame. Here we group this data frame by the source ID and show the matrix of experiment ID, variable ID, and table ID. And in this way, we can easily know how many GCM has the variable that we want. And also you'll notice that here I pass an argument, the require all on equals source ID. The function of this argument is to only include the models that have both variables, TS and TSMax. If we don't include this argument, the model that only has one variable will also be included here. We can view it as a data frame as well. There are many information over here. And intake-esm provides an extra functionality to directly load this data into a dictionary of X-ray dataset. Just use this toDataSite function of intake-esm. And what we get is a Python dictionary, and each element of this dictionary is an X-ray dataset. We can see that it tells us the keys of this dictionary will be structured as activity ID, institution ID, source ID, experiment ID, table ID, and a grid label. And we can prove that by listing the keys. And let's say if we want to access one of them, and we get the X-ray dataset, you notice that we have two data variables in this X-ray dataset, the TS and TSMax. Intake-esm works fine. It helps us to open multiple data stores simultaneously and combine them into an X-ray dataset. This is how intake-esm helps us to access CMIP6 data in the cloud efficiently. And thank you for watching. See you next time. This is how intake-esm helps us access CMIP6 data in cloud efficiently. Well, thanks for watching and see you next time.